So end behavior is basically what happens to a graph when x gets really, really big, goes to positive infinity, or when it gets really, really small, or goes to negative infinity. So we've, in our time looking at graphs, we've had the lines. The end behavior of this line, as x gets bigger and bigger and bigger, f of x goes off to infinity, positive infinity. As x gets smaller, goes to negative infinity. The line goes off to infinity. The function goes off to infinity. If we had f of x equals x squared, and we didn't know what it actually looked like, we know that as x gets really, really large, or goes to positive infinity, a million squared, a billion squared, a trillion squared, these are just huge, 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 huge numbers. And negative infinity, same thing. Negative a million, negative a billion, the values of the function just go off and off. We know that this comes down like that. Sorry for my poorly drawn graph, but basically what we want to know is what happens as we get way out here or way out here. A function like f of x equals x cubed, same deal. So as x gets very large, a million, a billion, a trillion, when you cube that, it's some enormous number, so it's going off this way. Negative a million, negative a billion, negative a trillion, when you cube those numbers, you get a very large negative number. So it goes off this way. To the values of the function. So let's take f of x equals 1 over x. And what's that going to look like? Well, as x gets very large, say a million, 1 over a million becomes a very, very small number, 1/1,000,000th. 1 over a billion, 1 over a trillion. So as x gets very, very large, the function values are getting very, very, very small. In fact, they're getting closer and closer to 0 without ever getting to 0. And this graph happens to look like this. An asymptote, the y-axis. And then as x gets large in a negative way, a negative a million, negative a billion, negative a trillion, 1 over that equals a very, very small number, very close to 0, but a negative number. So here the end behavior, as x goes to positive infinity or negative infinity, the value of the function is going to 0, getting closer and closer to 0. Or we can say there's an asymptote, a horizontal asymptote, at the line y equals 0 of the x-axis. Okay. Let's say I had a function f of x equals 1 over x squared. Function's always going to be positive, because x squared is always going to be positive, but the same thing happens. As x gets very, very, very big, a billion squared, a trillion squared, 1 over that is a number very, very close to 0. Same thing for negatives. As we got to very, very huge negative numbers, square it, you're going to get a number close to 0. Okay, so again, we have this horizontal asymptote at y equals 0 or on the x-axis. And in fact, what happens, let's say I've got a function x plus 2 over x cubed minus 1. Okay. What happens as the values of the function get very, very large? Well, as x goes to positive infinity, the top's going to get very, very large. It's going to be a positive number, and the bottom's going to be very, very large, also a positive number. So we have some positive number, but what happens? Well, as x gets to be a billion, a trillion, gobbledy-billion, whatever, some huge, huge number, the top is a huge number. But on the bottom, as you cube that huge number, the bottom's getting, while the top is a huge number, the bottom is a much, much, much bigger number. So what ends up happening is you've got a very large number over an exceedingly, exceedingly large number. So again, this ratio is going to 0. Okay, so yeah, it's a big number up here, but this is just so much bigger on the bottom because you're cubing that huge number instead of just adding 2 to it. And in fact, this minus 1 really means nothing. Say I've got a million. A million plus 2 and a million cubed minus 1. The 2 and the minus 1, they're meaningless. They're just kind of fluff. So really what's happening is, x over x cubed, what's happening is the bottom is far outpacing the top. So as x gets really big, the value of the function is getting closer and closer to 0. Okay? So small number on top, big number on the bottom, just like over in these situations. Little number on the top, big number on the bottom, you're getting to 0. Well, how about when x goes to negative infinity? Well, you're going to have a negative number on the top, and a negative number cubed is going to be negative, so you're going to have a big negative number on the bottom. That equals some positive number. But same way, you're going to get something small on the top, something relatively huge on the bottom. Again, f of x is getting closer and closer to 0. So again, you've got this asymptote getting closer and closer, but never touching it. And it's going to 0. So that's the end behavior. And in fact, if we take, if we're looking at f of x equals p over d, if the degree of p is less than the degree of d, y equals 0 will be that horizontal asymptote. Or the end behavior is that as x gets large to positive and negative infinity, the value of the function is tending towards 0. Let's take a look at some others. So let's say f of x equals x plus 1 over x plus 2. Okay, what happens here? Well, you've got some, we can find intercepts, vertical asymptote. What's the end behavior? What happens as x goes to infinity or as x goes to negative infinity? As we talked about before, so say you have some big number, 1 with 82 zeros after it. What happens to the top and the bottom of the function? Well, I've got this huge number plus 1, a huge number plus 2. The 1 and the 2 are relatively meaningless. Okay, it's a little bit of fluff. Really what's happening is the ratio of these leading terms, x over x. So a million, a billion, a trillion, the ratio of 1,000,000,001 over 1,000,000,002, it's about as close as you're going to get to 1. Get numbers bigger, this huge number with 82 zeros after it, that with a 1 at the end, 1, 82 zeros, and a 2 at the end, the ratio of those two is basically 1. It's as close to 1, you know, you're getting closer and closer to 1. So this ratio of leading terms, x over x, that's 1. So the function tends toward a value of 1. Or we could say there's a horizontal asymptote at 1. Okay, so graph of this function, we've got vertical asymptote at -2. When x equals 0, I've got 1 over 2, which is 1/2. Let's see, we've got with our x-intercepts when the top is equal to 0, so at -1, and we've got this horizontal asymptote at y equals 1. Our graph looks something like this. So as we go to negative infinity and as we go to positive infinity, the graph is tending toward this line y equals 1. And really what that is, it's the ratio of the coefficients of the leading term. So let's, another example, say 3x plus 1 over x plus 2. What does that look like? Again, as x gets really big, the 1 and the 2 mean nothing. Basically, what's happening is you've got the ratio of the two leading terms, 3x over x, which is 3. So f of x is tending toward a value of 3. Okay? So this graph will look, again, we've got -2 is our vertical asymptote. We're saying the horizontal asymptote is y equals 3. When x equals 0, function equals 1/2. The top will equal 0 at -1/3. So graph looks something like this. And again, you can see as x gets very, very large or very, very small, it tends toward a value of y equals 3. So in this case, if the degree of the numerator equals the degree of the denominator, you will have a horizontal asymptote, or the end behavior, the graph tends toward the value of, we'll say, a over b, which is the ratio of the leading coefficients. Okay, so here the degree is the same, leading coefficient of 3, leading coefficient of 1, the ratio of 3 to 1, that's the horizontal asymptote. Up here we had leading coefficient of 1, leading coefficient of 1, 1 over 1, that ratio is 1, the graph tends toward y equals 1. And this will work the same if you've got okay, I've got a quadratic on the top, a quadratic on the bottom, but as we get really, really, really big, I mean, numbers that we can't even fathom, perhaps, a 1 with 2,000 zeros after it, the 5, the 1, the x, the 2x are relatively meaningless. Really what's happening is this ratio of these leading coefficients, or these leading terms. Okay? So the degree is the same. So as x gets really, really big or really, really small, the graph is going, the value of the function is going towards 2/3, the ratio of the leading coefficients. So we'll have this horizontal asymptote of y equals 2/3. Okay, so what the graph is doing And so here's the line 2/3. The graph, as it gets out here, is heading towards 2/3, and out here it's getting closer and closer to 2/3. Right. So degree of the numerator is less than the degree of the denominator. We have an asymptote of horizontal asymptote of y equals 0, or the end behavior, the value of the function is getting closer to 0. When the degree on top and bottom are the same, we have an asymptote y equals the ratio of leading coefficients. Okay. So what happens if we have a function that looks something like this? Oh, x squared plus 3x plus 1 over x minus 2. Okay. So here now we have a degree on top that's larger than the degree on the bottom. So what's going to happen is, as x gets bigger and bigger and bigger and bigger and bigger, the top's going to grow and grow and grow. The bottom's not going to grow as quickly. What's going to happen, it's almost, the opposite, the inverse of what happens. When we had 1 over x, what happened was the bottom just outpaced the top by so much that it went towards 0. Well, if you flip these around, this top is growing so much faster than the bottom that there's going to be no bound to this function, the function value. So the function, as x gets bigger in a positive direction, it's going to just keep going, getting bigger and bigger and bigger and bigger and bigger. And as it goes to negative infinity, what's going to happen is, so this will go to positive infinity because we'll have positive over positive. If we've got a negative large number, the top is going to be positive because of this huge x squared. Bottom will be negative, so this is going to go off somehow toward, as we go off to negative infinity, the function value will get to negative infinity as well. Well, what's it look like in the middle? Well, we know we've got this, we're going to have a vertical asymptote at x equals 2. And also what we're going to have is an asymptote. Let's see if I can draw this with my fancy tool here. Let me adjust this just a little bit here. So we've got an asymptote, which I'm going to call an oblique or a slant asymptote. And we've got, wherever 2 happens to be, we're going to have an asymptote at x equals 2. But what happens is, if we look at the ratio of the top to the bottom, we looked at it before, the ratio of the leading coefficients when the degree was the same, when the degree was less on top than on the bottom, that ratio is going to 0. Well, here we've got the ratio of a quadratic to a linear equation. If I divide the top by the bottom, I end up getting x plus 5 with a remainder. But what I care about is this right here. No matter how big x gets, the ratio of the top over the bottom will roughly be x plus 5. So this ends up being the line y equals x plus 5. And the end behavior will be described by this, meaning the graph is going to tend toward this line as it goes to positive and negative infinity. And what happens with this graph ends up looking something like this. But what happens is, so there's no bound to the function values. So the range is going to be negative infinity to positive infinity, but as we get, as we go toward negative infinity, we go toward positive infinity, while the numbers get bigger and bigger, they're tending toward this line right here, which is y equals x plus 5, or the ratio of the top to the bottom. Okay, we've got f of x equals x squared minus 2x plus 4 over x plus 1. Again, there's going to be no bound for the function values. As x gets bigger, it's going to go off to, as x goes to positive infinity, the value of the function is going to go off to infinity. And as x goes to negative infinity, the function is going to go, the function values are going to go to negative infinity. So there will be no bound. However, there will be, so we've got an asymptote at vertical at x equals negative 1. When we divide x squared minus 2x plus 4 by x plus 1, we get x minus 3 with some remainder. But this line, y equals x minus 3, will be x minus 3. This line will be the slant or oblique asymptote. So the function will go off forever and ever and ever to positive infinity to negative infinity, but it will tend toward this line, y equals x minus 3. So we're looking at here where the degree of the numerator is 1 more than degree of the denominator, and we'll get some line, y equals something, numerator without the remainder. So here we've got x minus 3 without it. This divided by this is x minus 3 without a remainder. The one prior we had x plus 5 without its remainder, and that's where the graph tends to. This graph ends up looking something like this again. And again, the graph's going to tend toward this line.